Alright, so today's module we will talk about Green's functions. If you remember, in the previous modules we looked at the surface integral equations. We kept writing a function g, and we said that we will worry about it later. Now is when we worry about it. Okay. Right. So, this is a sort of outline of this module. We will first of all give a motivation for it, and after giving you the motivation for it, we will run through some simple 1D, 2D and 3D examples. Okay. So, to many of you it will be the first time that you are encountering this object called Green's functions. Okay. So, to give you some familiarity and comfort with it, I will give you all of these different examples. All right. Now, sort of the motivation for it is something that electrical engineers are already very familiar with, right, and that is the concept of a impulse response. So, everyone who has done first year of engineering, whether it is EE, EP or whatever, have seen signals and systems. So, what is the idea here? I send a signal xt through some LTI system, and I say that what is that LTI system characterized by? An impulse response ht, right. So, we will just assume that this is LTI, okay, a linear time invariant system. How do we characterize a response in time domain? If I want to express y in terms of x and h in time domain, it is a convolution, right. So, I just write it in time domain. I write this as yt is equal to the convolution of xt and ht. Pretty straightforward, and I mean, all of you will know by now that working in the time domain and a convolution is a little bit more painful. So, the more convenient way to handle it is frequency domain, right. So, in the frequency domain the convolution becomes product, right. So, this becomes y of omega is equal to h of omega x of omega. So, given any system, our first objective is let me characterize the system, means let me find out ht. Once I find out ht for a LTI system, life becomes very easy, because I either do the time domain version or the frequency domain version to get the response, right. So, the question is how would I calculate ht? What kind of a procedure would you follow for calculating the impulse response of a system? Y of omega divided by x of omega, right, and take the inverse Fourier transform. Okay. So, in other words, so we will do first is we will calculate y of omega for a known input x of omega, okay, and second is do a inverse Fourier transform, right. So, that will take h of omega to ht, or I can stay in h of omega in the omega domain itself if all my calculations are going to be done in the frequency domain. Now, this is the main thing that I want to calculate. So, what will be if I do not want to do any additional calculations, I just want to give some input to the system such that my output is itself the impulse response. So, looking at this equation, what is the simplest x omega you can think of?
Delta function.
Simplest x of omega? 1, right. So, if x of omega is equal to 1, then your whatever I get from the system output is itself going to be equal to h of omega, right. Now, what is the x of t corresponding to this? It is a delta function, right. So, if I put delta t into this function over here, right, the location of the delta function is included in the integral, and I am going to get a x of omega equal to 1, right. So, as a result, whatever y I have got, I call it the impulse response. Okay. So, this is something very familiar, right. Give a unit impulse to the system, whatever I get as the output is my impulse response. Okay. Same idea is being called by a different name, it is called Green's function, exactly the same concept. In signals I worked in time and frequency, now I will work in space and spatial frequency. Okay. So, that is the only slight difference. So, this Green's function is the same as an impulse response, there is nothing different. Okay. What will get generalized is in space I can talk of 1 dimension, 2 dimension, multiple dimensions, right. So, it will be a impulse response corresponding to so many dimensions, okay, that is the only idea. Now, when we looked at the surface integral formulation, you already saw that knowing that function g was very useful because it helped us to simplify everything else, right. So, let us just do a sort of a brief review of what we already know, but in a little bit more formal language. So, I am going to say that let us say that this L is some kind of an operator. This example of an operator can be let us say del squared, or it can be del squared plus k squared, depends on the problem, okay, whatever it is, let me call it L, and it is an operator. So, it acts on let us say some function, let us call that phi of r, okay, and I get f of r out of it, okay. So, now the sort of notation is clear to you, right. There is some operator which acts on some function and output is f of r, okay. Typically f is known to you, f is the given forcing function, okay, and I want to find out phi, okay. So, typically this is given. If it were the other way, if I were given phi, then it is trivial to calculate f, right. I just apply the operator on it and I get f. So, that is not very interesting. What is interesting is given f of r, find out what is phi of r, okay. The other thing I want, yeah,
What is the L operator? Is it some operator?
L is any operator, general, we are not getting into the specifics of it, okay, can be any operator, any like a differential operator over here, okay, plus some constants or whatever, or it could be something simply something like this, okay, we will keep it as general as possible. So, looking at this kind of a, let us for example take this, you can notice that this operator, the way I have written it, it only acts on unprimed coordinates. In fact, this whole equation has only unprimed coordinates in it, okay. So, I am setting it up for the case of the Green's function where one more coordinate comes in, the primed coordinate, okay, but we will just make a note now that L acts on unprimed only. So, now how do I define the impulse response? How did we define the Green's function earlier in terms of the language of L? Remember, we had last time an equation like this and we wrote a definition for G. So, how will you write that now? So, some operator L, okay, acts on G. G, remember, I have defined as a function of two variables, right. What should I equate this to? Delta, right. This is the definition of Green's function, right. This is the response of the system when the given input is a delta function, right. As we discussed that is the very definition of the system. So, in other words, the system response when the input is a delta function is called the impulse response, and in this the language that we are using now, it is called the Green's function, okay. So, so far we have not done anything fancy, we have just used definitions. Why are we assuming it is a LTI?
Why are we assuming it's delta?
We are assuming it is a LTI system. So, the impulse response will be the response to a delta input. L is like a, think of L just as for example like this, a differential equation.
System analogy.
Yeah, so a system can also be characterized by means of a differential equation, right. So, just think of it like that. Yeah, Dirac delta is the input and G is the response of the system to it, okay. It is that function which satisfies this equation, right. The only function that will satisfy this equation is the impulse response itself, hence the name in impulse response, okay. So, if I look at this system, so this is the input and this is the response, okay. I know that the notation looks a little different, okay, but it's, yeah, I mean its opposite means when I am trying to solve this problem, what I am actually formally trying to do is I am trying to find out, this is my objective, right, but I am writing it in this notation for now, Okay, so all your intuition of signals and systems carries forward over here. Okay, and this equation you have already seen once before when we wrote down for that wave equation, right? Remember we had del squared plus k squared, and we had acting on phi is equal to delta. Okay. So I have not put a minus sign over here. Previously we had a minus sign, so that's another matter of convention with these Green's functions. Some people will define it with a minus, some people will define it with a plus. Doesn't matter. Okay. Now this impulse response is, so if you are given the impulse response like in the previous slide, how do you find the response of the system? Convolution, right? Given ht, convolve it with the input, get the. Okay. So now if I am given g, right? So if I am given, now I am given g, what is phi? That's my question. Okay. In other words, I want to solve this equation formally. How do I do it? So if I call this equation 1 and call this equation 2, I want to use 2 in order to solve 1. So if you recall the tricks that we had used for that surface integral, what would you do? Multiply. In fact, this answer is simpler. Yeah. Okay. So So I multiply the second equation by what? If I multiply the second equation by f of r, why? Exactly, he has the right idea, right? So if I take 2 multiplied by f of, what should I multiply it by? Okay, let's start by saying let's multiply it by f of r. What will happen is, it's an operator, remember, so I am multiplying on the left hand side. Okay, so maybe I should, let me just write it like this, f of r into equation 2. So f of r, L g r r prime is equal to f of r delta of r r prime. Okay. Can this f of r move across this L? No. Right. What do I want? Fine. Okay, so as he suggested, the intuition is that if I multiply f of r and now integrate this delta function on both sides, what will the right hand side become? If it will become f of r prime, right? So I will get the RHS of equation 1 almost, but the left hand side does not look like L applied to something. It's f multiplied by L acting on something. So I am not exactly getting what I want. So is there a small change I could do? Multiply by f of r prime instead. So if I do this f of r prime, now L operator, it acts only on unprimed. So it's a constant as far as L is concerned, right? So L, for example, is d by dr. If I multiply r prime has no relation to r, right? So r can move all the way across this L operator. In that case, this becomes L acting f r prime g r r prime is equal to f of r prime delta of r r prime. And now, as has already been suggested, I integrate, right? So if I integrate, okay, over a region, what is important over here? I should include what point? R equal to r prime. Otherwise, I am integrating 0 on the right hand side. So this will become, and I am integrating over which coordinates? Primed or unprimed? Primed coordinates, right? Because then another reason is then I can move that integral past L, because L acts only on unprimed, right? So now integrate over primed coordinates. So this becomes that is the left hand side, and right hand side becomes right. Now if I look at this equation, so let's call this 3. So compare 3 3 and 1. What is the right hand side of these two equations? This is the same, f of r, f of r. What is the left hand side? L acting on something, L acting on something, right. So, if I just compare these guys, what can I say? So, you notice I took the impulse response and I did this integration, right. This integration is actually what you have seen in signals and systems to be convolution, okay, but this is a more general way of writing it. So, given the impulse response, given the input to the system f, I give you the output. So, all the hard work goes into finding out g. A lot of hard work will go into finding out g, that is solving equation 2. Once I solve equation 2, give me any number of different inputs, all I have to do is evaluate this integral, right. So, that is why this Green's function holds the same importance as the impulse response does in LTI systems, okay. It completely characterizes the system. Okay. What I have not mentioned in this very general derivation is that this Green's function should also obey the boundary conditions of the problem, okay. That is implicit in this. When we take the explicit examples, it will become clear how these boundary conditions are being satisfied.